to get her paper in Sigmod, she basically drove down the street to come here. Right?
Yeah.
Prior to that, she was a PhD student at Xinhua. So here's she can talk about her work on data-intensive tool development.
Thanks, Andy, for the nice introduction. So everyone, welcome to Houston. I'm Jia Zou from Rice University. So according to our study, only a small portion of tool developers develop their big data analytic tools from scratch or use low-level HPC and PI libraries. Most of them use a hyperductivity system such as Hadoop and Spark. Examples include SimCircuit, Giraffe, SystemML, Mahout, GraphLab, and so on. So systems like Spark and Hadoop, they provide users object-oriented interface that is based on languages such as Java and Scala, as well as a set of distributed high-level operators, which make them very convenient for developing distributed analytics on top of unstructured data. However, such a convenient interface also brings significant drawbacks in terms of tool development. So firstly, those systems are not declarative. They use opaque UDF to customize operators, which is not understandable to a system optimizer. So there's automatic query optimization is very limited in those systems. Users need to specify how to compute. Users need to tune tons of parameters and their application code for the best performance. So as a result, the tools developed on those platforms are not reusable with different input data or different underlying systems. This is a big pain point to tool developers. And secondly, those systems heavily rely on a manager runtime such as JVM, which takes over the management of objects. As a result, serialization, deserialization overhead are significant when moving complex Java objects across different processes. And such overhead is unavoidable in those systems. So big data tool developers, they deserve a better platform. We find that a good big data analytics tool should be highly reusable with different data, different hardware systems, and they should provide high performance to make critical decisions at the right time. And they should have low development cost so they can get to the market fast. So correspondingly, a good platform for such tool should have a declarative interface with data independence, should provide developers bare metal control of low-level systems for managing objects and memory directly, should have high productivity, providing an object-oriented and UDF-centric interface. So PlinyCompute is our solution to address this problem. It can meet all three requirements. It is high productive through its C++ binding. It's declarative in the large, providing relational style query optimization. User only need to specify what he wants, not how it computes. And it is native in the small. By removing JVM, it can provide various performance benefits. So next, we will describe PC's unique interface for how to create high-performance objects, non-opaque computations, and optimizable query graph, respectively, through examples. So firstly, how to create objects in PlinyCompute. So the goal is to remove serialization, deserialization overhead for moving objects across different processes. So in this sample code, user first will create a thread local allocation block that will be managed by an allocator that is transparent to developers. And then all subsequent invocation of method like make object will create PC objects in the same allocation block. And each call to make object method will actually return a handle that points to the created PC object. And the user can use this handle just like a C pointer, C-style pointer to construct complex nested objects. And in the end, user can send his object, which is a vector of employee objects in this example, to the remote PlinyCompute system for storage. And on the hood, actually, it is the allocation block sent to the remote node with zero serialization, deserialization for the objects in it. So how the objects in the allocation block can work after it is moved? So the main idea here is to replace the C style pointer using the PC's offset-based handle. So the C style pointer uses memory address that is specific to a process, which is not portable to a different process. But PC's handle is different. It uses an offset that is relative to its allocation block. So once the allocation block moved to a different process, all the handles in it can still work. So at the server side, we actually use buffer pool pages to serve as the allocation block. So once the page is full, it can be spilled to disk or shuffled over network without any serialization, deserialization overhead. Actually, there are a lot more ideas about PC object model for how to fix vtable pointers and how to have different allocation policies in the same allocation block, how to manage all those allocation blocks in the allocator. Unfortunately, due to limitation of time, we recommend everyone to read our paper to learn more details. So next, we will describe how to create computations in PlinyCompute. So the goal is to make UDF understandable to a system optimizer. Similar with Spark, in PlinyCompute, it also provides a set of high-level distributed computation objects, such as selection, multi-selection, which is similar with a flat map, aggregation, join, top case, scan set, write set, and so on. And all those computations can be customized by implementing user-defined functions. For example, to customize a selection computation, user needs to implement the getSelection UDF to specify the filtering condition, and it needs to implement the getProjection UDF to specify the transformation. So, but uniquely in PlinyCompute, you can use lambda calculus to implement UDF. Here we illustrated using a simple employee selection class. So in this getSelection UDF, make lambda from method larger than and smaller than are all templated C++ micro functions that are part of the lambda calculus interface. For example, make lambda from method actually extracts the member function from a given object. So, this getSelection UDF will be compiled into a unique lambda tree structure just like this. So a system optimizer can traverse this tree to understand what is going on. So the system optimizer knows the getSalary method will be invoked twice from the employee objects and compared to 5,000 and 10,000 respectively. Such knowledge gives the system a chance to do relational style query optimization. For example, in this case, it can remove the redundant getSalary method invocation. Next, we briefly describe how to create query graph in PlinyCompute. So in this example, we have 3 computations. One scanner that reads the input employees from a set, and the employee selection we just described. And the third computation object is a writer that outputs the filtered employees to a given output set. And the user can use methods to construct a cyclic query graph, and in the end, user can execute the query graph and to obtain the results. Based on the lambda calculus interface, the query graph will be translated into an intermediate representation, which we call TCAP, that is fully analyzable and optimizable by a system optimizer. In addition, by removing JVM and leveraging C++, we can provide high-performance execution of a query graph. So basically, we use 2 techniques. One is called generation, and the second is vectorized pipeline execution. But uniquely, those 2 features are all enabled by the C++ templated method programming. We will use an example to describe those benefits. So each query execution thread fetches vectors of employees from buffer pool pages iteratively. And in each iteration, it first creates a new vector called empty1 by running getSalary on each employee element in the vector. Then it compares each salary in empty1 with 5,000 and create a new Boolean vector called BL1. Then similarly, it compares MT1 and 10,000 and creates a new Boolean vector called BL2. Next, it compares BL1 and BL2 and applies the AND operator, creates a new vector called BL3. Finally, it filters the employee vector based on the BL3 value, and the filters output the employees that have a salary between 5,000 and 10,000, which are directly created in an allocation block. So in summary, for code generation, all the code for the executors, such as apply the get salary, apply the comparison, apply the AND, apply the filter, the code are all generated at compilation time through C++ templated metaprogramming. And each of those executors are processing a vector of objects at each invocation, so that the virtual function call overhead for running the pipeline can be amortized to a vector of objects. Now let's describe PlinyCompute, the distributed design. So it is a shared nothing architecture. It consists of one manager node and many worker nodes on each worker node. It has one front-end process that have a user-level file system as well as a buffer pool that is created using a large piece of shared memory using the mmap system call. And the backend process is forked to run the user code just like a query execution engine. And the backend process can directly access the pages in the buffer pool through shared memory without any that move that copy overhead. And the user once created a query graph. The query graph will be transparently translated into TCAP, which will be submitted to the manager node. On the manager node, a TCAP analyzer, which is also query optimizer, will optimize it into better TCAP and scheduled into a set of job stages dynamically scheduled to run on workers. And on each worker, job stage, such as the pipeline stage, will read data from the buffer pool, run the execution, output the data to disk for persistence, or send over the network for shuffling without any serialization, deserialization overhead. Right now, we have a full working prototype that is open sourced. We have developed a number of representative applications, which we will describe later. We have conducted a performance evaluation on an AWS cluster that have 11 instances, and each instance has 8 cores, 16 8 GB memory, 200 GB SSD as the EBS volume. So we start to describe our performance results from this LDA example. LDA is a short abbreviation for latent dirichlet allocation. It is a popular statistical topic generation algorithm. We invited a Spark expert to implement the same algorithm on Spark. And compared to the vanilla Spark implementation, PlinyCompute can achieve up to 25 times speed up. And later, after we do more tuning on Spark, like adding the broadcast join hints to the Spark implementation, which is specific to the data size of when we run this workload. And the Spark implementation runs much faster, but PlinyCompute can still achieve 6 times the speed up. And later, after we do more tuning on the memory or on the multinomial distribution, in the end, PlinyCompute is twice faster than a fully tuned Spark implementation. So we feel this case greatly demonstrated that the power of the declarative interface of PlinyCompute. Data independence actually means less or little tuning efforts. Similarly, we also achieved twice to 3 times speed up for GMM and K-means. We also invite a PhD student to implement linear algebra DSL, which works just like a distributed MATLAB. And this PhD student only takes 6 weeks of time, but the prototype achieved 1.5 times to 27 times the speed up compared with the state of art for 3 typical linear algebra algorithms, gray matrix, linear regression, and nearest neighbor, by using different dimensions of data. We also benchmarked 2 complex aggregations on up to 500 gigabytes to normalize the TP-CH data. So here, each customer object will have nested with a vector of order objects, and each order object will further be nested with the vector of line item objects, and so on. So for processing such complex and highly nested objects, PlinyCompute can achieve 5 to 66 times speed up. The coding overhead in terms of lines of code with PlinyCompute is acceptable and can be further improved by enhancing the tools and libraries. So in conclusion, today we present PlinyCompute as a better platform for developing and deploying your data-intensive tools. It is declarative in the large and native in the small. It is a combination of high performance and high productivity. It takes a PhD student only 6 weeks' time to develop a full functional and high-performance linear algebra library. And through a complete set of benchmarks, PlinyCompute can achieve up to 15 times speed up compared to Spark. So please visit our website to learn more. Thank you, everyone. Any questions? Thank you. Please go to.
Hi, great slides. So, one reason behind the popularity of Spark is the rich fault-tolerant mechanisms. So, and these mechanisms degrade somehow performance. So the first question, do you have any fault-tolerance mechanisms in your approach? And second question is, did you compare exactly the overhead on serialization in Spark with your approach?
Yes, very good questions.
Repeat those questions. Repeat them to the audience.
Oh, yeah. So the first question is whether PlinyCompute has any fault tolerance mechanism, because Spark uses lineage, something might degrade its performance, right? So for this question, actually, yes. In PlinyCompute, we have a heterogeneous replication mechanism. So the data will be replicated for high availability. And for the second question, it is, have we benchmarked the serialization, deserialization overhead in Spark and do a comparison? Yes. And we have some charts here. Yes. So we find that for manipulating super complex objects, like the normalized TPCH data, actually in Spark, up to 17 times could be spent in serialization, deserialization. So those overhead can be split into two parts. One is the closure serialization, deserialization for the Spark Java codes. And the second part is the RDD serialization, deserialization.
Okay, thank you.
Thank you very much.
Hi, thanks for the talk.
Thank you.
I was wondering, is this framework, meant to be like a low-level computational framework on top of which you build some DSLs for the end user, or is it meant to be used directly with this C++ interface that you showed?
Oh, could you please repeat your question? Sorry.
So I was, you showed some, overview of existing, TensorFlow's Spark, and you compared your tool with Spark a lot, and you said that the interface should be declarative. Mm-hmm. You showed that C++ code. Do you think it's declarative and high level enough, for data scientists to use directly, or do they need some kind of DSL on top of it?
Great question. Do you expect data scientists to write C++ code?
Yeah, because that, when you compare with Spark, I guess that code, if you show it to some data scientists, he'll probably run out of the room screaming.
Yeah, I think that's a great question. And I think so our platform is developed for tool developers. So at the beginning, let's see home, yeah. Okay, so here we actually compare to those tool developer platforms such as OS, native OS, HPC, MPI, Hadoop, and Spark. We are not comparing to those libraries built and tools built on top of those platforms.
Okay.
So our targeting audience, firstly, should be tool developers. Yes, maybe in the future, data science will also like to use our system. It's possible.
Okay.
Yeah.
Thank you.
Thank you.
So, what is this graph that you're measuring?
The popularity.
Based on what?
Based on the Google trend popularity for those different platforms.
This doesn't add up to 100% though, right?
No, let me see. No, 19, oh, 100.
So this is what you just, for some time, this is not important.
Okay, thank you. Okay.
What's your extensibility model? If you have like some other linear algebra implementation that somebody else implemented, say Intel give you a brand new, say Intel optimized cafe, how would you call it from inside PlinyCompute?
I'm sorry, could you please repeat?
How would you use externally written code from inside a PlinyCompute job?
Oh, you mean like how to port a user's existing code to PlinyCompute? So,
Let me rephrase the question. I come along with my Python package that I use for statistical analysis. I can throw that into pandas and do, run off panda stuff, or I can run it in Spark. How do I come along with some library to use your thing?
yeah, so I think one approach is to provide many domain-specific libraries on top of PlinyCompute. For example, we have one PhD student working on a deep learning library, deep learning tool on top of PlinyCompute. And he uses exactly the same interface with Cafe. So all the Cafe scripts can run on top of his tool.
Yeah, you can keep rewriting everything, but it just feels like having an extensibility model where you can incorporate existing code would be useful, right?
Yeah, I agree. Thank you.
Make it clear.
So I think, how do you ingest data if you have different data sources? And your data model seems to be an object store. So
Yes.
I can, let's say I model any real life object. I model a person and I model a school. And how do I put my relational data or CSV data to these two objects?
Yes. So firstly, you need to write up something like a parser to to transform your data into PC objects.
Yes. And how do you ingest data and you partition them to different cluster nodes?
So actually, at the manager node, there is a dispatcher. It will use multiple policies like random, like round robin, and like partition based on a UDF to dispatch your data to different work nodes. So this is transparent to the developers. You don't need to worry about it.
And
you only need to write like send data, and the data is distributed on the cluster.
And each object has a unique ID?
No, each object don't need a unique ID. So that's a lot of details about how we implement the storage, and we can discuss this offline. Okay.
Think of it again.
Thank you. Oh, I'm sorry.